हमारे चैनल बी ब्लॉग में आपका स्वागत है। दीपावली की हार्दिक शुभकामनाएं पहले तो सभी लोगों को, सबका जीवन अच्छा भी। आज हम पढ़ाने जा रहे हैं थर्मोडायनेमिक्स, जो कि एक इम्पॉर्टेंट चैप्टर है। इससे भी प्रश्न आते हैं। Thermodynamics is not the law of thermodynamics deal with energy changes of macroscopic system involving a large number of molecules rather than microscopic systems containing a few molecules. Thermodynamics is not concerned about how and at what rate these energy transformations are carried out, but it is based on the initial and final state of the system undergoing the change. Law of thermodynamics apply only when a system is in equilibrium or moves from one equilibrium state to another equilibrium state. Macroscopic properties like pressure and temperature do not change with time for a system in equilibrium state. The system under the surrounding. A system in the thermodynamics refers to the part of universe in which observations are made, and the remaining universe constitute the surrounding. Surrounding include everything other than system. System and surrounding together constitute the universe. The universe equal to the system plus the surrounding. Therefore, for all practical purposes, the surrounding are the portion of the remaining universe which can interact with the system. For example, if we are studying the reaction between two substances A and B kept in a beaker, the beaker containing the reaction mixture is the system and the room temperature where the beaker is kept in the surrounding. Types of system क्या होते हैं? ओपन सिस्टम, क्लोज्ड सिस्टम. इन ओपन सिस्टम देयर इज एक्सचेंज ऑफ एनर्जी एंड मैटर बिटवीन सिस्टम एंड सराउंडिंग्स. And closed system, in a closed system there is no exchange of matter, but the exchange of energy is possible between system and the surroundings. The presence of reactant in a closed vessel made of conductive material, copper or steel is an example of closed vessel. Isolated system. In an isolated there is no change of energy or matter between the system and the surroundings. Thermal flaw. The state of system. The system can be described in order to make any useful calculations by specifying quantitatively each of the properties such as pressure, volume, and temperature, as well as composition of the system. We specify the state of system by state function or state variable. The state of a system is described by its measurable or macroscopic bulk properties. We can describe the state of gas by quoting the pressure, its pressure value, temperature, amount, and variables like PVT are called state variable or state function because their value depend only on the state of the system, not on how it is reached. The internal energy as a state functions. It may be chemical, electrical, mechanical, or any type of energy you may think of. The sum of all these is energy of the system. In thermodynamics, we call the internal energy of the system, which may change when heat passes into or out of the system. What is done on by the system matter in interest or leaves the system work. We take a system containing some quantity of water in a thermal flask or in an insulated vehicle. This would not allow exchange of heat between the system and the surrounding through its boundary, and we call this type of system adiabatic. The manner in which the state of such a system may be changed will be called adiabatic process. Adiabatic process is a process in which there is no transfer of heat between system and surrounding. Here, the wall separating the system and the surrounding is called adiabatic wall. One way we do some mechanical work, say 1 kilogram by rotating a set of small particles and nearby churning water. Let the new state will be called B state and its temperature as TB. It is found that TB and the change in the temperature is that TB minus T delta T let the internal energy of the system in state B UV, and the change in external energy delta U equal to UB minus UV. We now do an equal amount of electrical work with the help of an immersion rod and note down the temperature change. We find that the change in temperature is same as earlier case, say T minus Tn. In fact, the experiment in the above manner was done by J.P. Joule between 1840 and he was able at 1840 he was able to show that a given amount of work done on the system, no matter how it was done, irrespective, produced the same change of state as measured by the change in the temperature of the system. Then the quantity, the internal energy, whose value a characteristic of state of a system whereby the derivative work WAD required to bring about a change of state is equal to the difference between the value of U and in one state and And then in another state, delta U equal to U2 minus U1, the positive sign is present, then WAD is positive when work is done on the system. Similarly, if you work in by the system, WAD will be negative. Heat we can also change the internal energy of a system by transfer of heat from the surrounding to the systems or vice versa without expenditure of work. This exchange of energy, which is a result of temperature difference, is called quantity. Let us consider bringing about the same change in the temperature, the same initial and final state as before in the section. By transfer of heat through thermally conducting walls instead of adiabatic wall. TA in container have a thermally conducting wall, say made up of copper and enclosed in a huge heat reservoir at temperature TB. The heat absorbed by the system Q can be measured in terms of temperature difference TB minus T1. In this case, change in internal delta is equal to Q. No work is done at the constant value. The Q is positive when the heat is transferred from the system surroundings to the system, and Q is negative when heat is transferred from system to surrounding. Delta U is equal to Q plus W, and Q and W can vary depending on how the change is carried out. However, Q plus W equal to delta U will depend only on the initial and final state. It will be independent of the way the change is carried out. If there is no transfer of energy as heat or as work, insulated W is equal to 0, Q equal to 0, and then delta U is equal to 0. And delta is equal to Q plus W is mathematical expression, a statement of the first law of thermodynamics, which states that the energy of an absolute system is constant. Applications work. For understanding friction balloon work, let us consider a cylinder which contains 1 mole of an ideal gas fitted into a frictionless piston. Total volume of gas is V1 and pressure of the gas inside is P. The external pressure is Px, which is greater than P. Piston is moved inward till the pressure inside becomes equal to Px. Let the change be achieved in a single step, and the final volume Vf. Cross-sectional area is a volume change equal to L into a delta V is equal to, we know the pressure force on the force on the piston pressure into area external. If work is done on the system by a system movement of the piston, then W is equal to force into distance Px Al Pa minus delta V. The negative sign of expression required to obtain conventional sign for W will be positive. It indicates that in case of compression work is done on the system, and here Vf minus Vi will be negative, and the negative multiplied by negative will be positive, and the sign obtained for work will be positive. A process change is said to be reversible if a change is brought out in such a way that the process could at any moment be reversed by infinitesimal change. A reversible process proceeds infinitely slowly by a series of equilibrium states, and such that system and surrounding are always in near equilibrium with each other. Processes other than reversible processes are known as irreversible processes. Internal energy of a system we can relate work to internal pressure of the system under reversible conditions by writing equations. W x equal to p x delta v into delta is very small. We can write it now. The pressure of the gas, which we write as p now, can be expressed in terms of its volume through gas equation for n volume and mole of an ideal gas. P is equal to nRT upon V at constant temperature. W equal to minus nRT upon free expansion of gas in vacuum is called pressure. No work is done during free expansion of an ideal gas, whether the process is reversible or irreversible. Enthalpy. We may write the equation as delta is equal to Qp minus P delta B at constant temperature, where Qp is the heat absorbed by the system and minus P delta B represent expansion work done by system. Let us represent the initial state by subscript and final state by 2. U2 minus Qp minus PV2 minus V1. On the energy we get Qp equal to Ut plus PVT minus U1 plus PV1. H equal to U plus PV. Qp equal to S2 minus S1. Qp is a path dependent function. Here is a state function because it depends on U, PV and V, all of which are state functions, and delta H is independent of path and Qp is independent of path. It is noted that delta H is negative for exothermic reaction which involve heat during the reactions, and delta H is positive for endothermic reaction which absorb heat from the surrounding. P is equal to nRT, PV equal to nBRT. Delta Ng is equal to number of moles of gaseous product minus number of moles of gaseous reactant. Delta H is equal to delta U plus NGRT. extensive and intensive property. And extensive property, the property whose value depends on the quantity or size of matter present in the system. For example, mass, volume, internal energy, enthalpy, heat capacity are extensive property. Those properties which do not depend on the quantity of size of the matter present are known as intensive property. For example, temperature, pressure are intensive property. Heat capacity क्या होता है? The increase of temperature is proportional to the heat transfer. The magnitude of the percent depend on the size, composition, and nature of the system. We can also see equal to C delta T. The coefficient is called heat of capacity. Large the given amount of energy heat results in only a small temperature rise. Water has a large heat capacity. A lot of energy is needed to raise its temperature. C directly proportional to the amount of the substance. The molar heat capacity of substance is the heat capacity for of substance and is quantity of inert heat needed to raise the temperature of 1 mole by 1 degree Celsius or 1 Kelvin Celsius. Specific heat is also called specific heat capacity. The quantity of heat required to raise the temperature of 1 unit mass of substance by 1 degree Celsius. For finding out the heat Q required to raise the temperature of a sample, we multiply specific heat of substance by the mass and m and the temperature delta T H equal to C into m into delta T. C delta T the relation between Cp and Cvy for an ideal relation. This is known as Mayer's equation. Cv minus Cv equal to R एट कांस्टेंट। धन्यवाद दोस्तों। चैनल अच्छा लगा हो तो पसंद और लाइक सब्सक्राइब करना मत भूलिएगा। धन्यवाद दोस्तों।